Good evening and welcome everyone to this lecture on the lunar South Pole environment. It's been given by Dr. Dan Batcheldor from Florida, and it's for the Herschel Society and the Bath Royal Literary and Scientific Institution. My name's Tony Symes, and I'm the organizer for these lectures. First thing to note is this lecture is being recorded. Now I need to remind everyone to keep their microphone on mute and their video off during the lecture. You can turn it back on again after the lecture for the Q&A session, but please keep your microphone off during the lecture. It's very disruptive if it's not. If Zoom stops for you, then just restart everything and I'll make sure you get admitted back into the lecture. Now, during the lecture, you may have questions. The best thing to do is to put the question in the chat channel, and then at the end of the lecture, we'll review all the questions in the chat channel and any that get added afterwards, and we'll deal with them then. Now, the next lecture for the Herschel Society is going to be on the 1st of October, and for that lecture, we're going back in time to look at Mars through Victorian eyes. So the lecture is called Life on Mars Question, a short history of 19th century exploration of the red planet. It's on Friday the 1st of October, and it's going to be a real physical lecture in the BRLSI, but also transmitted on Zoom. So when you buy tickets, you have to select which kind of ticket that you want. It'll be very exciting to welcome some of our audience back to the BRLSI. Now, I need to put in a plug just for another lecture, which is not a Herschel Society lecture. It's being given in the BRLSI on Monday. Again, this is a hybrid lecture, so you can either go to the BRLSI if you can, or you can buy a ticket for remote lectures. This lecture is on just checking the title, The Life and Science of Marie Curie, and it's by Dr. Peter Ford. I want to plug it because Dr. Peter Ford used to be the chairman of the Herschel Society. So that's Monday the 13th of September at 7:30 p.m. You can attend either in the flesh or buy a Zoom ticket if you're interested. Now, coming back to tonight, I'm very pleased to have Daniel Batcheldor here, on Zoom, who's been a good friend to the Herschel Society and the BRLSI, having given us lectures great lectures in the past in 2014 and 2018. He was educated here in Bath, and his career has taken him to Florida, to the Florida Institute of Technology, and now NASA's Kennedy Space Center. Let me hand over to Dan.
Well, thank you very much, Tony. I presume that you can hear me okay?
I can hear you.
Excellent. So we'll assume everybody else can as well. Well, thank you for that introduction. It's wonderful to be here. Thank you all for joining me. As Tony pointed out, I'm Daniel Batcheldor. I actually went to King Edward's School. I was one of the last cohorts that actually went through the North Road campus, and hopefully we will finally get some closure on what's going to happen to that building going into the future. But I then went on to the University of Hertfordshire, just in Hatfield, and got my undergraduate and graduate degrees in astrophysics before moving to upstate New York, actually, a place called Rochester. And then in 2010, I moved down to Florida and worked at a university down here. And for the last year and a half, I've actually been working at NASA's Kennedy Space Center for the Southeastern Universities Research Association, which is a conglomeration of universities with a common goal of advancing research in space sciences and particle physics. Now, today I'm going to be talking about the lunar South Pole environment, and this is of particular interest, of course, to NASA, as one of NASA's missions is to actually land the first woman and the first person of color at the lunar South Pole over the next few years. And so what I want to do is to go through what that environment is going to be like for those astronauts, and some of the problems that they are going to face, and some of the approaches that we are currently taking at NASA's Kennedy Space Center to mitigate some of those issues that we know they're going to be experiencing. The first thing I'd like to do, however, is to bring you all up to date with what it is we actually know about the moon. And we're going to start off with the orbit of the moon here with this lovely graphic from the Goddard Space Flight Center. What you're seeing here is the Earth-facing side of the moon. The actual south pole of the moon, confusingly, is at the top of the picture here. But what we can see is the names of all of the craters going by on the terminator. The terminator is the line between the dark side and the sunlit side of the moon. And you can also see here where the Apollo landings were, and they are at a very different location than at the lunar south pole. What we can also see is what's known as the eccentricity of the moon's orbit around the Earth, which means sometimes the moon is closer to the Earth. Sometimes you hear that called a supermoon, and sometimes the moon is farther away from the Earth. So that creates a kind of magnification effect, and you can see that in the image as the moon gets slightly smaller in the image and then slightly bigger as a result of that eccentricity. What that also means is that sometimes the moon is actually accelerating slightly towards the Earth and decelerating slightly away from the Earth on those particular points on its orbit. And you can actually see that manifested in what's known as the libation of the moon, which is where you can actually see when the moon is actually approaching the Earth, you get to see a little bit more of the leading edge of the moon. And when it's receding, you get to see a little bit more of the other edge of the moon. And this actually allows us to actually see more than just one half of the moon. And we can actually see just a little bit more, about 3% more of the surface of the moon than we would normally if it were on a completely locked orbit around the Earth. There is also a little bit of wobble because of the inclination of the lunar orbit as well. So sometimes we see a little bit more of the South Pole, and sometimes we see a little bit more of the North Pole, depending on where in the orbit the moon is as a result of that inclination. You can also see down here how fast the Earth is spinning day by day, the actual position of the moon relative to the Earth here. And you can also see the position of the Earth relative to the lunar sky. So where the Earth would be if you were standing on the surface of the moon. And then you can also see that yellow dot there is the position of the sun as it would be on the lunar sky. So if you are standing on the surface of the moon, it actually takes 2 weeks for the sunrise to sunset. So that would take 2 weeks for the sun to actually rise and set. But the Earth is always going to be in relatively the same position when you are on the sky, when you are standing on the surface of the moon. And so this is important because if you are standing anywhere on the surface of the moon that is facing Earth, you will always have a direct line of sight to the Earth, which means you have direct communications with the Earth at any time if you are on the near side of the moon. So that's important for operations on the surface of the moon when we need communications back and forth. So, of course, we've actually had people physically explore the moon. And so we've got images here of the successful landings on the lunar surface, the Apollo missions, Apollo 11, 12, 14, 15, 16, and 17. And you can see here that the technology advancements and the exploration capabilities that were actually developed during the Apollo missions go from Apollo 11, where it was simply a demonstration, essentially, of the ability to safely land a human, or 2 humans in this case, on the surface of the moon and return them to Earth. But this was just a few hours of a mission and relatively little scientific exploration was done in this case. It was mostly a technology demonstration, but there were quite a few particles and rocks returned from Apollo 11. The technology capability demonstration was increased with Apollo 12, as Apollo 12, as we'll see a little bit later, actually landed very near a spacecraft that had already landed on the moon a couple of years earlier, and that was the Surveyor 3 spacecraft, another NASA mission. And the objectives of the Surveyor 3 spacecraft were to actually make sure that it was actually safe to land on the moon in the first place. There was actually some concern that the surface of the moon was too soft, and that you would have significant sinkage into the surface of the moon because of the powdery nature of the surface of the moon. The Apollo 12 missions, which we will look at, the Apollo 12 mission, which we will look at in more detail, also was the Apollo mission where the sun was actually fairly low in the sky. The sun actually was only 7.5 degrees above the lunar horizon at the time of the first Apollo 12 EVA, extravehicular activity. In Apollo 14, we've now got an advancement in the spacesuit technologies. We've also got an advancement in the exploration capabilities. And you can see here, we've got even more capabilities during the later missions, where we've got the rovers themselves allowing a much more extensive exploration of the lunar surface. And you can see the culmination of the exploration actually ended up with Harrison Schmitt, the astronaut that you can see here. He was actually a scientist rather than a test pilot, and he was a geologist. And so he has the wonderful experience of being the only scientist to have ever visited the surface of the moon. But you can see him standing next to a house-sized boulder on the surface of the moon. So as a result of the human exploration of the moon, we know that there are some significant challenges to lunar exploration. And those challenges present some risks. And what we are trying to make sure of by working at NASA and at the Kennedy Space Center is we reduce as much risk as possible so that we can safely return these humans to Earth once their mission has been completed. And so the significant risks that I'm going to talk about today are twofold. First, the risk from the dusty surface on the moon, and then the risk from the sun angle. So the actual elevation, the altitude of the sun. And this is going to be particularly challenging at the lunar South Pole, where the elevation of the sun is always going to be very low. And so this, of course, is the iconic footprint image from Apollo 11. But this is a much less well-known image, but most likely much more important, demonstrating the imaging challenges from Apollo 12 simply because the sun was very low on the horizon. So, the dust. It was soon apparent that the dusty surface on the moon creates an operational challenge for the human exploration of this body. And we knew immediately from the videos taken of the Apollo landings that the descent engines underneath the lunar modules, the limbs, actually were interacting with the lunar surface and accelerating the particles on the surface of the moon in much the same way as you've likely seen the landing of the core stages of SpaceX's Falcon 9s back here on Earth. There's a lot of dust that gets kicked out. Well, that is particularly a problem on the surface of the moon, as there's no atmosphere on the moon to slow these particles down. They do not puff out into a cloud. They simply go on ballistic trajectories all around the moon. But what we have been able to do is do analysis of the Apollo landing and indeed launch videos to actually look at the change in luminosity through the window of the landers using a 72 millimeter video camera and determine exactly, place constraints on the actual density of the regolith, of the dust that was kicked up. We also know that the dust was kicked up simply by astronauts walking around on the surface and roving around on the surface. And you can see here, even with a rover that's going relatively slowly, there's a significant upkick of dust as a result of exploration activities themselves. Here we see the ascent of one of the Apollo missions, filmed from one of the rover vehicles. And so you can also see here a change in the luminosity as a result of this engine interacting with the lunar surface. And here we have a fairly iconic image of Gene Cernan after he had returned from exploring the lunar surface, and you can see the dust adhering to his spacesuit and actually getting in and around the cabin and in on his skin. And so this dust being tracked back into the ascent modules and here back into the command module once they had returned to lunar orbit is a significant concern, not only to the operations itself of the spacesuits, because this dust actually gets into the articulating joints of the suit and it actually damages the fabric of the suit, but also this dust is something that gets in the eyes of the astronauts and was actually inhaled as well. So we're not sure of the medical problems that would be created by having a significant amount of dust being brought back into, say, an Artemis capsule or an Artemis base that's on the surface of the moon after crew have been out on EVA activities. Now, coming back to the actual physics of how the moon's surface is impacted by the space environment, we know that the moon, of course, is exposed to the solar wind in a significant way. There is no significant magnetic field on the moon like we have here on Earth to protect the surface from the outflows of the sun. And that atmosphere also means that the moon is getting the full solar flux, which consists of the range of energies of photons, the particles of light coming from the sun, and also the solar wind, the plasma, the electrons and protons and neutrons that are coming from the wind, the sun itself. And so both these charged particles and these particles of light impact the day side of the moon. And as a result, the interactions between these charged particles and the lunar surface itself means that the actual day side of the moon gains a net positive charge, which actually enables dust particles that have a slight charge to potentially levitate slightly off of the lunar surface. Now, downwind, in the wake of the solar wind that the moon creates, we have what's known as a void in the plasma field itself. So the solar wind plasma, in this case, there is an actual difference between the thermal energy in the electrons. They have a lot more energy than the protons. The electrons are a lot smaller, of course. And so it's much easier for the electrons to quickly fill in this plasma void and actually provide a significant negative charging of the lunar surface. And these charges actually change, of course, as the moon's surface rotates into and out of the sun, so from the day side to the night side. And so we have measurements from orbit of the moon demonstrating that there is a significant charging taking place in the lunar environment. And so this can actually create dust particles that can levitate off of the surface. There is also meteorite activity. So there's also meteorite activity, and there's no atmosphere to slow down these meteorites as we have on Earth. On Earth, the relatively thick atmosphere actually decelerates meteorites into the phenomenon that you see as shooting stars or meteors, but these meteoroids actually slam into the lunar surface itself and also create a source of dust that can then populate the lunar exosphere. So we know of physical mechanisms that can also kick up dust, so that when astronauts do land on the surface of the moon, a lot of the dust that may be in that environment could actually be naturally occurring rather than simply be occurring from the landing that took place and the activities that they have. So this dust is a significant concern. We've also got evidence of there being a thin dust cloud around the surface of the moon from the Surveyor missions, the Clementine missions, and then actual sketchings done by the Apollo astronauts themselves. And so here we're seeing images from the Surveyor missions So Surveyor 3 is the one that Apollo 12 landed near, but there were many other Surveyor missions that successfully landed on the surface of the moon. And here we're seeing some video stills from Surveyor 7 showing that there is a glow on the lunar horizon. And this lunar horizon glow is consistent with there being a thin layer of 10 micron particles just above the surface of the moon. Excuse me, I've got a dry throat. So this type of lunar horizon glow was also seen from orbit of the moon, from lunar orbit, by the Apollo crew. And here we've got some hand sketches of that type of glow that was seen by the Apollo astronauts. We've since had many orbital missions around the moon that have also detected this lunar horizon glow. In this case, we're seeing results from the Clementine mission. And you can see that lunar horizon glow there. And this bright spot back here is actually Venus. So much like in the lunar environment, one of the brightest objects on the sky is Venus, as it is here on Earth. But this type of glow is inconsistent with zodiacal light. Zodiacal light is actually the dust left over in the solar system after the solar system was formed, and that can actually form a relatively similar phenomena, a glow on the horizon. But the actual morphology of this glow is inconsistent with zodiacal light. So there is some other dust in and around the lunar environment causing this scattering of the sunlight. So the levitation of dust has also been reproduced in the lab. And so we've got some results here from the University of Colorado, where the team led by Wang and collaborators actually took some simulated lunar materials, placed them into a vacuum chamber, and then bombarded those materials with the same plasma and electrons that the solar wind puts out. And so you can see here stills from a video that demonstrate it is possible to get particles to levitate in a vacuum environment simply by exposing them to the same type of particles that the lunar surface is exposed to because of the solar wind. So from the results of the electrons and protons impacting the surface, you can see here that you've got particles on ballistic trajectories. And we've also got the effects of UV radiation actually smoothing out the surface of this simulated lunar environment. So right now we've got evidence from in situ measurements in the lunar environment that there is a significant amount of dust kicked up from human activities. And we've got physical basis for, and we've got observations that support dust actually intrinsically in the lunar exosphere as well. And we've now got physical confirmation of the physics behind what could produce dust in the lunar exosphere as well. And there are many, many conferences that are dedicated to understanding the dynamics of lunar dust because of not only the scientific interest, but the operational interest as well for safely operating on the lunar environment. And so here we've got a nice graphic. This is completely made up. This is not a real, this is not a real image, but this is the type of bombardment that would be expected from a meteoroid activity. So in this case, you can see the exchange of momentum between small particles hitting the lunar surface rather than being burned up in the atmosphere of the Earth. And we've got more observational evidence consistent with there being a significant population of particles in the lunar exosphere as a result of micrometeorite bombardment. And so here we're seeing some results from the LADEE experiment, the Lunar Atmosphere and Dust Environment Explorer, which is a NASA mission that actually went and orbited the moon, counting how many particles impacted that spacecraft and where those impacts took place and at what time those impacts took place. And what LADEE determined was that there was a higher density of particles over the terminator of the moon. So that's the separation between the day and the night side of the moon. And there was also an increase in the particle density that coincided with known showers meteors. So these blue lines here correspond to known meteor showers from Earth. And of course, a meteor shower is when the Earth's orbit actually passes through the low density remnants of a previous comet. And so, for example, we can see here the Geminids, and there was a peak in the density measured by not only the density, but the charge as well, measured by LADI. And so these data are consistent with there being particles ejected into the lunar exosphere as a result of micrometeorite impacts. Now, the dust is not just a risk for lunar exploration. It is also a resource. So the technical term for the dust on the lunar surface is regolith. And regolith is actually a term applied to any dusty surface on a body like the moon or asteroids or even Mars, of course. It's not soil. Soil on Earth actually contains biological materials that we haven't detected on any other solar system body. But what we have been able to deduce about regolith is that it can contain a significant mass by weight of water. And so there are observations consistent with there being water present in regolith. And so there are a couple of measurements that have been made using neutron spectrometers, and there's physics behind why you get a neutron signal from interactions with the hydrogen in water. But for right now, we've actually seen not only from orbiting neutron spectrometers, but also from what's known as the L-cross impactor. There was another NASA mission that actually purposely crashed part of a spacecraft into the lunar surface to see what was kicked up. And there's signals consistent with the presence of water equaling about 10% by volume of there being water in the position that the L-cross impactor actually hit the lunar surface. So how you could have water existing in and around regolith, it could be existing actually in pores. So we call this pore ice, where you can see the distribution of water here in blue. And you can also have this interstitial ice, where you've got water essentially clinging to the surfaces of the regolith particles themselves. And so this is either water potentially distributed in the spaces between particles or actually clinging to the grain boundaries themselves of the regolith. And so there may be significant amounts of trapped water also on the lunar surface, both existing in craters, particularly where the crater has a significant time in shadow or is permanently in shadow, and where water may also be trapped below the surface, as well as existing in the pores or the interstitial regions between the particles themselves. And so we have a lot of evidence to suggest that there could be a significant amount of water on the lunar surface. We've also got recent evidence to suggest that this water may actually be in tiny little shadowed regions on the lunar surface as well. So it may not simply be all at the lunar poles where there are more regions of permanent shadows. And we can see here the distribution of water abundance with latitude. So we got previous data that have shown a significant uptick in the water abundance as we get to higher latitudes, but some more recent work have shown that there's more isotropic distribution of potential water sources away from the poles as well at the lower latitudes. And the way that data is determined is there's a very significant emission line. So you can look at the spectra of the data coming from the lunar surface, and this red peak here is consistent with there being a water molecule. So you can only have this peak at 6.1 microns if there is water present producing that return spectrum. Now, water, of course, is important for exploration because it is hydrogen and oxygen, and those are the principal components of liquid rocket fuel. And so water can be used as a source of refueling rockets on the surface of the moon. When you look at the big orange tank that was attached to the shuttle, and when you look at the big orange tank that forms the core stage of NASA's Space Launch System, that is actually two tanks. One of them is containing liquid oxygen, and one of them is containing liquid hydrogen. And the actual propulsion system is the controlled recombination of the hydrogen with the oxygen. And of course, the white plume that you see from launches of the space shuttle is water, not only from the noise suppression system, but water from the recombination of that rocket fuel. So it's important to find sources of water for refueling. And of course, it's also important to find sources of water as that can be, the oxygen can be used to support sustained presence on the surface of the moon. The water can be used for all sorts of other things, of course, including maintaining crew hydration and also producing crops on the surface of the moon as well. So it's a big deal to understand where the water is. So the dust on the moon is not necessarily just going to be a problem, but it can also be a resource. So moving on to the angle of the sun. Now, here we can see the iconic image from Apollo 11, the boot on the moon. And this image here, because of the known sun angle, actually allows us to analyze this image, because we know the size of the boot print, we know the size of these shadows, and it actually allows us to use the geometry of the sun to determine the depth of the footprint. But what we're seeing here, first of all, is that the boot sunk significant way, several centimeters into the lunar surface, that there is an incredibly fine powder. You can see how smooth the boot print is, and that the regolith itself is very coarse. So what we're seeing here is a very well-defined footprint, because the regolith particles are very jagged and they do not collapse easily as a result of the non-uniform shapes of these particles. It's not like sand at all. So just from this image, you could use the sun angle to and the geometry of the sun angle to determine quite a lot about the regolith itself. One other effect from the sun angle is that when you put your back to the sun, or there's any object around which light is diffracted, you get what's known as zero phase backscattering, which is essentially combined with the particles on the lunar surface and the effects of light refracting around this solid object. In this case, it's the astronaut, of course. You get this significant increase in intensity down in the anti-solar direction. And so we've got a huge contrast ratio difference between the lunar surface ahead of the astronaut and the shadow of the astronaut itself, whereby it's very difficult, nigh impossible, for the astronaut to actually see the ground directly in front of where they are moving. So you can imagine trying to traverse the lunar surface in this direction, being blinded by the surface itself and being unable to see what it is you may be treading on, a rock or a small crater or something like that. So we know that the sun angle is going to be an issue. And even more so, that issue was demonstrated by the Apollo 12 mission. And so here we're returning to the image I had before, whereby the sun, being very low on the horizon, completely saturates the camera, creates all sorts of optical effects, these optical halos, also from diffraction through the optics of the lens being used. But it is incredibly difficult. You've got some lens flare there, but it is incredibly difficult to make out features on the lunar surface. And you can actually read the transcripts from the Apollo missions. And from Apollo 12, you've got the astronauts very concerned with and actually experiencing falling over in unseen craters because of the difficulties from the contrast ratios from the low sun angle. Here you can actually see the zero phase backscatter effect even more in Apollo 12. So we've got an astronaut standing here taking the picture, and here's the actual shadow of the limb, the lunar module itself. And one of the issues that the astronauts experienced with the low sun angle was judging distance. And so on the lunar surface, the horizon is actually very close to you because the moon is much more compact than the Earth. And the horizon is only about 2 to 3 kilometers away, depending on what your elevation is, whereas here on Earth, it's about 5 kilometers away. But here, this shadow is actually 130 meters long, being cast on the lunar surface. And the astronauts actually completely misjudged the distance based on them thinking that this shadow was a lot shorter. And so there's some operational challenges with orientation and traversing the surface with regards to ranging on the lunar surface itself. So here is another pair of images from Apollo 12. Apollo 12 landed relatively precisely, believe it or not. That was actually part of the demonstration capabilities, that they could actually control with precision to within a few hundred meters of where they landed. So they purposefully landed near the Surveyor 3 spacecraft. And when they landed, the sun angle was, as I've mentioned, at 7.5 degrees. And they looked out across Surveyor crater. And so the sun here is actually creating a shadow on the inner rim of that crater, and you can just make out a Surveyor 3 here. Now, on first inspection from the window of the lunar module, the astronauts thought there's no way that they're going to be able to get to Surveyor 3 because this is an incredibly steep side to the crater rim, and it's not something that they could walk over safely. But they actually had 2 EVAs on Apollo 12, and by the second EVA, the sun had actually risen to 12.5 degrees, and the shadow had disappeared. And once the shadow had disappeared, they actually found that the slope of the crater was actually only at 14 degrees. They thought it was a 40-degree slope when they first inspected Surveyor 3 in shadow, but when they actually saw it in the full sunlight and the shadow had disappeared, that slope confusion had disappeared, and they were actually able to accept the risk of actually going over to Surveyor 3 itself and inspecting a spacecraft that had been on the lunar surface for several years. Now, going back to the challenges of the sun angle itself, the moon rotates once every 27.3 days, which means instead of there being a day of 24 hours like we have here on Earth, where the sun gets back to the same position in the sky every 24 hours, the sun takes 27.5 days thereabouts to get back to the same position on the lunar surface. And that's what creates the phases of the moon, right? Now, what we're looking at here is the lunar South Pole. Right in the center of this image, where you should be seeing the red laser pointer, that is Shackleton Crater. And the precise geographical location of the lunar South Pole is where the pointer is right now. So north is everywhere in this image because we are looking at the lunar South Pole. But it's this 10, 11 o'clock position on Shackleton Crater that is one of the positions that is of significant interest to NASA for several reasons, both having to do with the dust and the sun angle. So the first operational challenge is being able to see. So we don't want the crew landing in a region which is permanently in shadow, because there will not be a natural illumination source for them to be able to see what they're doing. And the actual temperature of that region is likely to be only a few tens of Kelvin, several hundred degrees below zero. So that will also create an operational challenge from thermal management, from managing the temperature necessary to keep equipment running. But also power systems are very well developed for spacecraft that are near enough to the sun to actually use the solar flux, the output from the sun, for photovoltaic power generation. So these are solar panels, right? So if you land somewhere where there's a lot of sunlight, so sunlight that is not appearing and disappearing every 14 days as the sun rises and sets, but a position on the lunar surface where you experience a significant amount of sunlight, maybe for 90% of the lunar day, then that is an excellent place to land, because you will almost always have a power source through solar panels. And so the lunar South Pole is of significant interest because it's one of those positions where you will not be going into and out of the day-night cycle every 14 days, but you could be in a region that has significant amount of lighting. And so here we see the shadows of a full lunar day. So you can see as the sun moves around the sky, you can see the length of these shadows, and you can see actually that there are regions that are in permanent shadow. And those are the regions where the temperature is incredibly low, and that is where significant amounts of water ice are thought to exist. So this is one of the major reasons why, these are the major reasons why the lunar South Pole is the target for human exploration. It is excellent for lighting, both in terms of the amount of light that we get to do solar power, and it is also excellent in terms of the lighting in terms of permanently shadowed regions that may contain the resources necessary to sustain a human presence on the lunar surface in the form of water held up in the dust that is in these permanently shadowed regions. So here is a look at the illumination conditions of Shackleton Crater and the regions around Shackleton Crater. So regions that are blue corresponds to the percentage of time that there is no sunlight, and regions that are red corresponds to regions that are in near permanent sunlight. And so you can see here that the rim around Shackleton Crater is not only in near permanent sunlight, but is also close to regions that are in near permanent darkness. Just to give you an idea of scale, the Shackleton Crater is actually 20 kilometers in diameter. And you can see the actual scale in kilometers across the bottom and the side here. So this is a fairly big image. So while it might look like this is a very narrow region around Shackleton Crater, we'll zoom into it in a moment to actually show how diverse the lighting conditions there are, making it an excellent place for human exploration. So zooming in a little bit, we can see here the illumination conditions in several regions. So we've got the Shackleton rim. So the X marks the actual lunar South Pole itself. But here we've got the rim, which has got a significant amount of sunlight. And then we've got these bridge regions here, C1 and C2, these connecting ridges that have also got a significant amount of sunlight. One reason they have a significant amount of sunlight is the lunar topography is actually very diverse. And the lunar South Pole itself is actually at an altitude of 1.2 kilometers. Well, these connecting ridges here are actually at an altitude above the lunar radius of 1.9 kilometers. And so they are above any other surface features that may actually produce shadows. And so this is why they're getting a lot of sunlight. And so zooming in on these regions, you can see that not only is there a high portion of direct sunlight, but there are also permanently shadowed regions in and nearby. And so for a crew landing in a permanently sunlit region, they don't have far to go to traverse over to regions that they want to explore in order to determine and extract water ice. So we are actually working at the Kennedy Space Center, and I'm actually working on two specific missions designed to determine the risks to and enable the exploration of the lunar surface, particularly at the South Pole. So one of the instruments that I'm working on is called LEIA. That is the Lunar Environment Imaging Apparatus. And that actually builds on some recent work that I was doing before I joined NASA on advanced high contrast ratio imaging. And when I was still at the university, we were applying that technology for searching for exoplanets around stars. But that same technology can be used in order to enable the exploration of the lunar surface, particularly when you've got regions with that high intensity zero phase backscattering and lunar shadows themselves. We're also developing an array of instruments called ALARM, the Advanced Lunar Array for Regolith Monitoring. And so these are several deployed sensors that will be looking not only at the regolith that is kicked up as a result of human activity from the landers and from people kicking the dust around as they explore the surface, but actually the natural exospheric dust concentration as a result of interactions with the solar wind and interactions from the micrometeorite bombardment. And so the last talk I gave back in Bath, I think, was actually on the payload that we launched in 2017. And so this was the payload that I led. This is a picture of it actually after it came back to Earth. Yes, it wasn't burnt up in the Earth's atmosphere. We actually landed it back on Earth and got to take it to pieces, and that was fun. But here you can see the payload being deployed on the NanoRacks external platform on the International Space Station, where it spent 8 months gathering very, very boring looking data. But this is the data actually from the payload, and it actually demonstrated that the sensor that we were using inside that payload actually has an extreme contrast ratio capability. So instead of the typical sensors that you would get in your cell phone or something like that, this sensor has technology on it that enables it to have an incredible dynamic range of 92 decibels. Compared to a typical dynamic range of around 70 decibels in off-the-shelf imaging devices. So this is what I talked about last time I was with you all. So this is my last slide. And so as in summary, the lunar South Pole environment has complex electrostatics as a result of the interaction with the solar wind. If you're remembering back to that picture where we've got a slight positive charge on the daylit side of the moon and a significant negative charge on the dark side of the moon, well, the lunar pole is actually very close to the terminator between the two. So we expect an incredibly complex electrostatic environment there that could actually have an increase in exospheric dust around the poles. And that dust actually can create operational issues. The dust can get in the articulating joints of spacesuits. It can scratch up the visors. It can actually inhibit docking mechanisms and latching mechanisms. And it can be tracked back into the habitats where it could get in the eyes of astronauts or be actually breathed in. But the regolith, the dust itself, can actually be a resource. We want to mine it, to use it for an in situ resource in terms of rocket fuel, the hydrogen the oxygen also for breathing, of course, and the water for all of the other things that humans need water for. And then, of course, at the poles, the sun is going to be permanently at a very low position on the horizon. On average, the sun is actually going to be only at 1.5 degrees above the horizon at the lunar South Pole. The sun, of course, is only half a degree in angular, it projects only half a degree angularly on the sky itself. And so this is going to create a lot of very large, long shadows that confuse people that are traversing around on the surface. And so we're addressing these types of risks from this contrast ratio problem between the sunlit and the dark side of the lunar surface using high contrast ratio imaging. Right, so I think that does it for the slides that I have. And so I see that there are a few questions in the chat, but we have Tony to go through those questions for us that I'll be happy to answer over the next few minutes or so. So thank you for your time.
Thank you very much, Dan. That's it's fascinating to think of how we could be progressing towards landing people in this area. So I think we've only got one question in the channel now. Do indicate if you have any more questions. What I'll do is I'll get you to read out your question, and then Dan can deal with it. So first of all, if we could go to Deepali, you had a couple of questions.
Hi, thanks. Yeah, my questions actually relate to the water formation, because the first question that arose in my mind was that while water is a good resource for refueling in terms of the oxygen content and the hydrogen content, my brain tells me that how these particles exist on the South Pole region of the moon is as elements. So, I mean, I just can't understand how water vapor can be forming there. My second question relates to the problems of the contrast and the intensity of the reflection from the moon's surface, and how the Apollo 11 mission dealt with it, because they didn't seem to report that problem.
So as to your question about the origin of water on the moon, It's actually the same question for the origin of water on Earth. And so there are several explanations that can account for the presence of water on the Earth that are actually analogous to the presence of water on the moon. And those two arguments are either water was here on Earth to start with, or water was delivered here to Earth during the early history of the Earth itself from objects that are known to contain water that come from the icy outer regions of the solar system in the form of comets. And so for a long time, it was thought that the water on Earth was actually delivered to Earth by comets. And so if it's delivered to Earth, it's actually delivered to the moon as well, because the Earth-Moon system is actually a very unusual system, because there's the mass ratio between the Earth and the moon is actually quite low. Whereas normally the mass ratio between a planet and its moon is actually quite high, for example, Jupiter and anything else. So it was thought for a long time that because we've detected water in the halos and the tails of comets, and we know that the Earth has been hit by comets in the past, that the water was actually delivered that way. However, it could well be now that Earth was actually formed at a time where either the solar system was a lot cooler, so water could exist on the surface while the atmosphere formed, or the Earth was actually formed much farther out in the solar system where ice could exist. And then as the solar system dynamically settled, the Earth actually migrated in, and the water then from ice turned from ice into the liquid water and the water vapor that we experience mostly here on the surface of the Earth. So the same mechanisms can account for the presence of water on the moon as well. It can be there from the formation of the left over there from the formation of the moon, and it can also be delivered to the moon as well. Now, with the moon, that water being in regolith and the regolith being transported around the surface of the moon means that it actually can conglomerate in regions that have incredibly low energy. So in physics, systems are actually always trying to get in thermal equilibrium. Is one of the fundamental laws of thermodynamics. Everything's always trying to be in the same temperature as everything around it, right? And so systems seek out the lowest energy situation. And so as these regolith particles are transported around the lunar surface by bombardment with other micrometeorites, or through the levitation process as a result of interaction with the solar wind, we have actually got explanations for the transport of regolith around the surface, and therefore the transport of water around the lunar surface. But it's important to realize that this is not like water that you have in your cup of tea, right? It's water that's actually ingrained within the materials themselves. And so it's not just a question of picking up the water and putting it in your hydrolysis machine and getting your hydrogen and oxygen out, or using it for it needs to be processed out of the regolith, and one way of doing that is simply by heating it up. And so this is what we mean when we say volatiles, is something that actually can get into a gaseous state with the addition of some heat. And so yes, we do understand. We have several mechanisms to explain the presence of water on the moon, and those are analogous to the explanations that we have for the presence of water on Earth. Apollo 11 was actually landed during a time where the sun was actually relatively high in the sky. And so the sun was much more overhead during Apollo 11, and the contrast issues were not as severe during the Apollo 11 missions. So this is why I highlighted Apollo 12. Apollo 12 is the only mission where there was a low sun angle during the initial operational phases of that mission. But they landed and were on the surface for several days. And so by the time they got to their second EVA, the sun was actually at a much higher angle, and they have a direct comparison between operations at a low sun angle and operations at a bit less of a severe sun angle. And so the intensity issues of Apollo 11 were not felt as severely as they were for Apollo 12, simply because the sun was about 30 or 40 degrees above the horizon, and not getting in the eyes of the astronauts and creating huge long shadows. Yeah, but thank you for your questions. They're good ones.
Thank you very much.
Okay, Charles, then, please. Charles Draper. Charles is asking why the South Pole rather than the North?
The North Pole, of course, also has all of the same conditions, but it's quite interesting to compare the topographical maps of the lunar surface from the South Pole and the North Pole. And when you look at the North Pole compared to the South Pole, there's a lower density of fully sunlit regions in proximity to permanently shadowed regions. So there's a much higher density of landing locations that are much more conducive to surface operations at the lunar South Pole. And so, yes, the North Pole was looked at for quite a while, but it's simply there's a lot more opportunity at the South Pole when it comes to scientific exploration and the use of natural resources that are at the South Pole. But that's a great question. Yeah.
Perhaps I could slip one in here. I'm interested to know how the astronauts would use this high contrast imaging to deal with the lighting conditions on the surface of the moon.
Well, there's several ways that they could use that. First is by robotic exploration, so that the next generation of rovers that go onto the lunar surface actually have this high contrast ratio capability where they can, at a distance, take an image of the side of a crater with the bright rim of the crater in the same field and still get good signal from the interior of the crater. So whilst they are called permanently shadowed regions, they are permanently shadowed from the sun, but they are not completely dark. They are actually illuminated by scattered sunlight from other regions around the crater rims themselves, and they're actually illuminated by our own zodiacal light. They're actually illuminated by our galaxy as well. And so they are actually receiving a very low very low flux of light themselves, much as we do at nighttime here on Earth. And so whilst they are called permanently shadowed regions, that shadow is strictly the shadow of the sun, but they are not completely dark. And so you can actually see into those permanently shadowed regions if you have a camera with a high enough sensitivity. But if it's too sensitive to deal with the brightness of the lunar surface around that, then you actually have to switch to the camera that we're working on, which is the camera with the incredible dynamic range. But yeah, great question. Right. So they could use them on rovers. They could use them as a handheld device as well, so that when they're actually going around the lunar surface, they can use it to take a picture and then inspect that picture to actually pick out details that they wouldn't be able to pick out with the human eye.
Okay, that sounds interesting. Yeah. Andrew Ward, would you like to ask your question? I'm giving everyone a moment to read their question out if they want to, but to keep things going, I'll read it out myself. Is the lunar axis exactly 90 degrees to the sun all year?
No, so it's not like the Earth where we've got a 23.5 degrees tilt to the rotational axis of the Earth with respect to the orbital plane. With respect to the orbital plane of the moon around the Earth, it's actually tilted at 1.5 degrees. So there is actually a slight tilt to it, which does actually mean that even at the pole, the sun is going to wobble up and down slightly. So if you are standing at the lunar South Pole, monitoring the sun, it's actually going to disappear behind some mountain ranges and then pop out again and slightly dip below the horizon for just a short time every lunar year, which is why going to actually a slightly higher altitude gets you above that and into a region where you have a direct line of sight or almost direct line of sight to the sun all year round. So yes, there's a 1.5 degree tilt. So it's not precisely at 90 degrees to the sun.
Okay, back to Charles Draper. Charles, are you online to ask your second question?
Looks like he's talking, but nobody's hearing.
Right. Well, I wonder if something... I'm just checking to see. He's not muted, so I don't know why we can't hear him. So his question is, could the electric charge on the particles be used to help a cleaning mechanism to protect astronauts?
Yes, it can. And actually, that's some technology that has been developed by the Kennedy Space Center known as an electrostatic dust shield. So in that case, the charges on the particles are actually used to move the particles off of a surface that is embedded with electrodes. And so there are some excellent demonstrations of this technology from the electrostatics lab at the Kennedy Space Center, where electrodes have been embedded between two plates of plexiglass, and then those electrodes have been used to generate a magnetic field on the surface that actually then accelerates away those charged particles from the surface. So yes, that technology is being used and developed in order for cleaning of particular surfaces. So it's first being looked at for solar panels, but it's also being looked at for visors and windows and things like that. Yeah, but yes, it can, in answer to your question. Yeah.
Chris Bullen, would you like to ask your question?
I'm not sure. Is this working?
Yes, we can hear you.
Yes, it is. We can hear you. We can hear you.
Okay. Two questions, really. The first is, how much water is there, and do we know how deep the water-bearing zone is? And the second question, which comes back to the question of actually when did the water arrive, what is the age of the Shackleton crater?
So in terms of the volume of water, it has been estimated that about 10% of the volume, of the mass, which is about 5% of the volume, actually is water itself. So if you took a volume, so if you just dug up a volume of regolith, about 10% of that is going to be the water itself. So those are estimates that have been made by remote sensing. So that is where you use natural cosmic rays to essentially interact with the water and produce what's known as a fast neutron that is then detected in orbit by spacecraft. And so that's the detection mechanism that has been used in many of the cases. The other way of doing it is to actually illuminate the region where you think there's water and look at the reflected spectrum that you get back. And the reflected spectrum can include spectral features that are consistent with the presence of water molecules. And then the strength of that spectral feature can actually tell you about the relative the relative concentration of those molecules as a result of that. But we have not yet gone to robotically or using humans to dig up a region of these permanently shadowed craters to actually demonstrate how much water can be got from it. And there are several upcoming missions that are aiming to do that. It is a big open question, is how much regolith do you need in order to produce a certain number of liters of water? And there are estimates that range from not much to all of it. So, so that's a very big open question, and one that will be answered very early on in the Artemis missions. As for how deep it goes, we anticipate that there are surface deposits in the form of the ice in between the pores and in the grain boundaries, but there may also be deposits, as there are on Mars and on Earth itself, that are subsurface. And the only way that we would determine the presence of those is using a technology known as ground penetrating radar, which allows you to determine the change in density of a material based on the radar response that you get from sending those radar signals into the ground. And so the surface regolith itself is fairly, for the top few centimeters, the overburden is relatively easy to pick up. But after about 10, 15, 20 centimeters, the density of the regolith increases quite a lot. And there's some very interesting videos of the Apollo astronauts trying to hammer in the flagpoles into the ground, because they can push it in for a few centimeters, but then it gets very difficult to push it in because of the rapid change in density of that lunar material. Now, the change in density of the regolith is thought to be from essentially the shaking of the moon. So as the moon is cooling, it's actually contracting slightly, and that creates very low-level moonquakes. But the moon is always being bombarded with micrometeorites and those types of vibrations, much like when you, if you want to, pack down some sand here on Earth, you can actually increase the density by tapping it down, right? And so that's thought to be a process for actually compacting the regolith itself. So yeah, the depth of the regolith, the water-bearing materials could be quite deep, but the actual region that you could process of the light, fluffy material is likely to be on the order of tens of centimeters, not more than a meter or so. I hope that answers your question, Chris.
It does.
Great.
What about the second one, the age of the...
Oh, the age of Shackleton Crater. I don't know off the top of my head. Somewhere around 1 billion years, right? So, interestingly, you can age the lunar surface by counting craters, right? So a well-defined crater that has no other craters in it is going to be a young crater, because there has not been time for another impact to happen after that impact, and there's not been time for the regolith to actually smooth over those craters, and so it's a whole field of study is from crater analysis of the lunar surface to age the lunar surface itself. In terms of Shackleton Crater, it's quite interesting, of course, because it's a polar impact and it's a very round, well-defined crater, and it actually only just has a slightly flat floor, and so it's a very interesting crater. And there will be an age for it that we can look up after here, but everything's about 1 billion years old, right?
Right. Deepali, you wanted to ask another question.
Yeah, thanks. I'm just going to have to read it out. Hello. I was just wondering, all the stuff that is being planned by NASA to happen on the South Pole, on the lunar South Pole, needs a lot of technological development, particularly the photo imaging and the processing of the water, because, assuming that water exists where it's thought to exist, how is it going to be, extracted for use? So I'm just wondering where we're at in terms of all of this technology.
So at the moment, this technology is here on Earth, and we are just waiting for a private company to come up with a lander that can place it on the surface of the moon so that we can carry out those tests. And so the technology readiness levels are actually mapped at NASA, and you can go ahead and look for technology readiness levels. And it's a way that we determine how ready a technology is, how prepared it is in order to carry out the mission. And so something at a technology readiness level of 1 is essentially an idea that somebody's had. Technology readiness level 2 is that they've demonstrated that their idea essentially may work. And so we've got a lot of technologies that are at TRL, technology readiness level 6 or 7, which is we've demonstrated that they work here on Earth, and we are now just waiting for a ride to get to the lunar South Pole. And so one of the significant shifts in the way NASA has operated in the last decade or so is that it's shifted responsibility for the delivery of vehicles to low Earth orbit, to the International Space Station and beyond, to the private sector. And it's now focusing on these types of questions, the technology development questions to support the human exploration of the solar system, and the technology development necessary to answer these fundamental science questions that we have. And so there are technologies now that have been built and are ready to go at the Kennedy Space Center that are drills that drill down into the regolith with a corkscrew that actually brings up the regolith into an oven. That oven then bakes that regolith, and allowing the water to be evaporated from that. That water is then put through what's known as a cold finger and allows it to condensate, and you can actually measure the amount of water that would come out from a known core. And so
that's on Earth, though.
They have demonstrated that here on Earth. Yes. It is not. It is not yet flown
in my mind.
Yeah, on the moon.
In my mind is is not a plus point, because the conditions in the moon and everything else. I mean, it's totally different. So how can we say that the process that we've perfected on Earth will work on the lunar surface?
Well, we simulate the lunar surface back here on Earth. So one of the facilities at the Kennedy Space Center is a large test bin that contains lunar regolith simulant that was actually recovered from a mine back here on Earth. And that's actually 120 tons of the lunar regolith simulant. And so surface operations are actually tested using the same type of material that actually the lunar regolith is made from. So there's very coarse material with a known particle size distribution. So we know how many particles are this big, how many particles are that big, and we've actually got a big test facility here at the Kennedy Space Center actually to carry that out. We can also reproduce the thermal and vacuum environments as well in chambers. And there's huge chambers that NASA operates in order to do full-scale testing of, for example, the James Webb Space Telescope, which is now scheduled for launch December 18th of this year. And so the hardest thing to reproduce is the gravity environment of the moon, but that can be done using the zero-G spacecraft. And so we are able to reproduce the physical conditions of the lunar surface back here on Earth. But as you point out, that's not a perfect analogy. And so that's why, with these technologies, we don't say that the technologies work just yet. But we've tested them as much as we can here on Earth. They have been demonstrated to the point where they can be sent into the actual environment to carry out a full demonstration mission. At that point, they would be at TRL 9, Technology Readiness Level 9, which is the technology has been deployed in the actual environment and been shown to work.
Which countries are sort of above the TRL 6 level at the moment?
Well, a technology readiness level applies to a particular technology, not to a space agency. But the technology readiness level is a technology mapping scheme that NASA uses. I'm not sure what is used at the European Space Agency or the Indian Space Agency or the Chinese Space Agency or the Russian Space Agency. But no doubt they have a way of documenting how well their technology is progressing towards full operations. Yeah.
Right. I'd like to ask you about the comparison between the regolith on the moon and on Mars. I understand that the regolith on Mars is highly oxidized and therefore very toxic. I imagine that's quite different from the lunar regolith. Is that right?
The toxicity of the Martian regolith is something of relative concern. Yes, there's not only the oxidization taking place, which in and of itself is not necessarily a bad thing, but what's been discovered in the Martian regolith is something called perchlorates, which are sort of salty deposits that can be toxic themselves. So the major difference between the moon and Mars is the moon has been geologically inactive for many billions of years, 2.5, 3 billion years. And the surface has simply been churned away by the interactions with the solar wind and impacts with the surface itself. Whereas Mars has been geologically inactive only for the last billion and a half years. And so its surface is a lot more diverse in terms of the processes that have taken place. For example, you see the evidence for previous water deltas on the surface of Mars, which you don't see on the moon. You see on the surface of Mars evidence for dormant or past volcanoes on the surface of Mars, which you don't see on the moon. So there's a lot more surface processing that has happened on the Martian surface. There's also a thin atmosphere, of course, so the transport of dust is known to take place on the Martian surface, because we have pictures of it taking place, right? We've got dust devils and planetary-wide dust storms. And so while the regolith could be fairly isotropically distributed on the moon, the regolith is also the overburden, the very top layer of regolith on the surface of Mars, is also going to be well distributed, but it's likely to be much more diverse than what we see on the moon. But in terms of the toxicity, the actual carcinogenic issues with the lunar regolith that we're concerned with, the actual abrasiveness of the particles themselves that are of primary concern. But I'm sure somebody is looking at some of the higher level biological interactions that could be happening with some of the volatiles that may be present in the lunar regolith at lower quantities than we know there to be water present.
Right.
Yeah.
Well, that covers all the questions that we have, and it just remains for me to say that this has been a really fascinating lecture. I mean, I knew a little bit about the dust on the moon, but nothing much, as much detail as Dan has gone into. I knew nothing about the problems with the light. That's entirely new to me. So it all helps point the way to perhaps a successful Artemis mission in the future. So it would be really great if everyone could unmute themselves and give Dan a round of applause to thank him for such a great lecture.
Thank you, everyone. Thanks. Appreciate you being here.
Thank you.
Thank you.
Well,
Thank you.
Thank you.
Wonderful.
Right.
Very exciting. Fascinating.
glad to hear it. Yeah, thanks.
Well, good night, everyone, and we hope to see you again soon.
Thank you.
All right. Bye, everyone. Thanks for joining.